So in this session, we'll go over an application of cycles. We already have seen power plant cycles, and we have considered several examples as a conventional Rankine cycle, the regenerative one, Rankine with reheat, etc. And in all of these applications, the purpose was to use heat to produce work. Okay, we'll see now that in a very similar cycle, we'll do just the opposite thing. So we'll put work on our system in order to impose heat motion from cold to hot place, which is the unconventional way. Okay, so in any problem, in any new problem, I will always describe for you the situation and you will have all information required to build your cycle. Okay, so for example, I can tell you that for your refrigerator, your system is composed of 4 components: a compressor, an evaporator and condenser, and an expansion valve. So I will tell you this, and then you can easily build your system. Now, when we will discuss what is happening, you will be able to know, when I give you the properties, you will be able to put the place of your equipment appropriately and draw the corresponding TS diagram, okay? Because when we say we have a refrigeration application, so as we mentioned in the refrigeration application, our purpose is to force heat to go from cold to hot, okay? This is why the place of your evaporator and condenser will be switched relative to a power plant cycle. In a power plant cycle, the evaporator phenomena will take place at the hot temperature, and the condensation will take place at the cold temperature. Now it will be exactly the opposite, because what you want to do, you want to extract heat from a relatively cool medium. So Qn in the evaporator will take place at the lowest temperature, at T cold, okay? And the rejection of heat at the condenser will take place at the highest pressure and temperature level. So this is the main difference, if you want, between the two systems. Plus, instead of a turbine, the turbine produces work in general. Here you will put work on your compressor, because you will provide electrical work in order to be able to extract heat from the cool place and reject heat to the hot place. So we have here W dot N to the compressor, Q dot N at the evaporator level. If we take the refrigerator example, the evaporator is from the inner side of the refrigerator, and the condenser will be from the outer side. So if you turn your refrigerator and you put your hand, you will feel the warm sensation because you have rejection of heat from this side. Okay, so this is the whole idea. Plus, here, of course, we'll not put a turbine for the expansion, because in general we put the turbine in order to have a production of work. Here we don't want this. We want to have minimal loss of energy. And in the theoretical case, we can consider that in our expansion valve, we don't have loss of heat and work. And I will tell you then that the expansion valve will allow you to do expansion as constant enthalpy. So this is the property of expansion through an ideal expansion through this throttle valve, which is H equal to constant. Okay, so once we describe this, you will be able to build your cycle, and we can consider now the TS diagram, which will allow us to solve whatever we want. If you want to calculate, here we don't talk about thermal efficiency. Instead, we talk about a coefficient of performance, COP. And as we discussed before, we can talk about two COP, coefficient of performance for refrigeration and coefficient of performance for heat pump. So it depends on the applications that you have. If you want to use the cycle for refrigeration purpose, then what you care for is to increase Q dot N, because you want to increase the heat extracted from your cool medium.
Hello?
Yes? Do you hear me? Okay. So here, Qn will enter the evaporator, and this is the important heat that we want to produce here, because we want to extract heat from the refrigerator. So the COP of refrigeration will be simply a Q dot N over the input here. The input here of energy is W dot N. So we should do Q dot N over W dot N. While if our purpose is to produce heating effect, and let us consider HVAC systems. HVAC systems during winter will play the role of a heat pump. So then the COP of heat pump will be Q dot out over W dot N, while during summer, they will play a refrigeration role. So their COP will be Q dot N over W dot N. And also we related already in previous sessions together, we said that we can relate COP heat pump to COP refrigeration because COP heat pump is equal to Q dot out over W dot N. And then since Q dot out is related to Q dot N, you know that if we take the whole cycle, if you consider the whole cycle, we can write for the whole cycle that sum of Q, so sum of Q dot equals to W dot net. And since here we neglect any work at the valve level, so we can say that it's equal to Q dot N. Q dot N minus Q dot out is just equal to W dot N. So, sorry, Q dot out minus N, because here you know that sum of Q equal to sum of W. Okay, equals to, but here since we are putting work on the system, okay, so it's equal to minus W dot N. Because you know, in the convention, sum of Q equals sum of W. You consider that W is positive when it's produced by the system. When you put work on the system, you consider it as negative. Okay. Or also you can, yes.
If it's Q out minus Q in, it's work in positive, right?
Yes. If it's Q out minus Q in, you will put W dot N. So it depends. Okay. It depends on the convention you take. Okay. If you take the convention sum of Q dot equal to sum of W dot, when you write this, you consider that the work is positive when produced by the system. Okay, because what is the main equation? dE by dt, the storage of energy. Okay, dE by dt is equal to sum of Q dot minus sum of W dot. But when you consider the whole cycle, so you go to the same point, dE by dt is 0. Okay, so for a cycle, since you reach the same point, the energy is the same. So this term will drop out. Okay, and you end up with sum of Q dot equals sum of W dot. But you should keep in mind that you use this convention. So when you put minus here, this means that the work is positive when produced by the system and negative when you put it on the system. This is why here I considered minus W dot N. And if you take now a W dot N to the other side, okay, you will deduce that Q dot out equals to Q dot N plus W dot N. Another convention will tell you that everything in is positive, everything out is negative. Then you put, if you want to do this convention, you will put plus here. And at the end, whatever you do, you will get the same result. Because if you put a plus here, you will go back to Q dot out equal to Q dot N plus W dot N. Because everything in will be positive then, and everything out will be negative. So whatever is the convention you take, this will not affect your final result. Okay, just respect the convention you take in the equation and you will get exactly the same result. This convention is easier, I think. You can put sum of Q dot plus sum of W dot equals 0. Everything in is positive, everything out is negative. So you put plus W dot N plus Q dot N minus Q dot out equals 0. So you get that Q dot out is equal to Q dot N plus W dot N. You can do this always. So this is why COP heating is larger than COP refrigeration. Because if you replace, you deduce that if you do COP refrigeration plus 1, you will get COP heating of the heat pump. Okay. Now for the HVAC system, it will work in both ways. During winter as heat pump, during summer as refrigerator. But here our application is different. We are considering a refrigerator. So we just care about COP refrigeration. Okay. So our purpose will be to calculate Q dot N and W dot N. And then we can find the coefficient of performance of our system. This is why I need to provide you with enough information to construct your cycle. Okay. In general, for example, of course, they will give you the pressures. They will always give you the low and high pressure. And here, as we mentioned, it's different from the power cycle in terms of location of condenser and evaporator. So the evaporation will take place at the low pressure level. So for example, if I tell you the evaporator pressure is 100 kilopascal, while the condenser pressure is 800 kilopascal. Okay. In addition, I should give you information about the states for compressor and the expansion valve. So we can say, for example, let's say I tell you that at the compressor outlet, for example, you have a temperature of 50 degrees. And at the compressor inlet, you have a temperature of, let's say, minus 20 degrees. And I tell you that at the outlet of your condenser, you have a saturated liquid state. So this will be enough for you to draw the TS diagram. Okay. So now we just have to draw the TS diagram, put what we know, and deduce all our other unknowns. Okay. So let us draw together the cycle. So here we should pay attention, okay, that why we used a compressor instead of a pump, because in the power plant cycle, the pumping process will take place in the liquid zone. This is why we use a pump. While here, the increase of pressure will take place in the vapor zone. This is why we use a compressor. And you can check this from the condition given. Okay, so let us say you don't know this. You don't know that the compressor will work in the vapor zone. You can verify from the conditions they gave you, because they gave you a 0.1, which is the inlet of the compressor. The conditions are as follow. They told you that the pressure is 100 kilopascal. And the temperature is minus 20 degrees. Let us say we don't know this state, okay? we can check from the tables. Of course, I should tell you the type of refrigerant. Okay, so let us say here we are using the refrigerant, which is 134A. In all thermodynamic tables, in any book of thermodynamics, you can get the tables at the end. Okay, so for example, here we have the tables. We can check the tables here. We go for refrigerant 134A. Okay, for example, here we have an appendix telling us that for for 134A, we have the saturated tables, temperature entry, pressure entry, and we have the superheated refrigerant. Okay, to check, we want to check that this point is in the superheated region. So all we have to do is to consider the pressure, which is, as we said, 100 kilopascal, and a temperature of -20. So they told us that for superheated 134A, we go to table A12. So let us go to table A12. Okay, this is the properties of superheated refrigerant 134A vapor. Since the pressure is 100 kilopascal, and you know that 1 bar is 10 to the power 5 Pascal, so 100 kilopascal will correspond to a pressure of 1 bar. So we are here. Okay, we can check for the saturation temperature. We have that the saturation temperature from this table is minus 26.43 degrees. So we can say then that our temperature, which is minus 20, is larger than T saturation. So we can be sure that we are in the superheated region, since minus 20 degrees is larger than T sat. So this is the right table we are searching for. And since our temperature is minus 20 degrees, so we can read here the enthalpy value at the inlet. Okay, so from here we can find the value of H1. H1 at the inlet of the compressor is 236.54 kilojoule per kilogram. And in case you need any other property, okay, what do we need, do you think now? What is the other property we might need?
Entropy.
Exactly, the entropy S, okay? In case, for example, in general, when they don't say, if they don't give us any information, we can simulate, we can model this process as isentropic. And we say that S at point 1 is equal to S at point 2. But in case they gave you, if you want, the temperature at point 2 at the outlet of the compressor, then they might consider that we have some losses, and that's why they will give you the value. But if they don't give you any information, you can say, I will model the process as isentropic, so S1 is equal to S2. So check for what you have, okay? In case they gave you the temperature at the outlet of the compressor, then you use it. So you use the temperature given, since you know the pressure. Let's say the outlet pressure is given 800 kilopascal. If they give you the temperature, for example, if they tell you the temperature at the outlet is 50 degrees, you can directly from the table determine but not for this table, of course, because the pressure is higher. So if they tell you the exit pressure is 800 kilopascal and the temperature is 50 degrees, you should go to the pressure of 8 bars. So if we continue here, if we go down, we search for 8 bars. Okay, and in this case, for any temperature, we can check for H. Okay, but in this case, if they give you the temperature, this means that it's not an ideal process. It's not isentropic. So if it is not an isentropic, they should give you enough information to be able to calculate your state. So they will give you the temperature. But if they don't give you the temperature, yes.
Here, if they gave us the temperature at the outlet of the compressor,
yeah,
do we consider it as isentropic? Because you wrote down, right?
No.
S1 is equal to S2.
No, because if they give you the temperature, this means
We can
that
find
yes, there will be a contradiction, because if they tell you, for example, the outlet temperature is 50 degrees, okay, while at 8 bars, in case it's S is constant, we will check the temperature will be different. So if I impose on you the temperature, then you cannot say I will model it as isentropic. So there might be some irreversibilities. This is why they give you the temperature. Okay.
Thank you.
So if they give you the temperature, you use it. You have the pressure 8 bar, you have the temperature 50. You say, then let me go to the table and determine the enthalpy at the exit, which is, let's say here, H2 equals to 284.39. Okay. But in case they didn't mention the temperature at the outlet, so you don't have any information, then you can model the process as isentropic, and then you should go back to your table here and say, let me take the value of S, because S1 should be equal to S2. If I go to 1 bar again, I say for this temperature of minus 20 degrees, I have that S is equal to 0.9602, and it should be equal to S1. S1 equals to S2 in order to be able to consider state 2. So S1 equals S2 equals to 0.9602. And if we check now together, this will correspond, okay, to another temperature different than 50. Because if it's isentropic, okay, the temperature will be, can you tell me if it's isentropic, the temperature will be smaller or larger? Who can tell me? You remember, whenever we talk about isentropic process, okay, this means that we don't, yes, it's reversible. We don't have any entropy generation, okay? Whenever we have entropy generation, this means that we'll have an increase in temperature. So instead of going straight, so if I illustrate it, we'll illustrate it in the graph, okay? But let us check now. If I take isentropic process S1 equal S2 equals to 0.96, I should go back now to my table of 8 bar. Okay, and I will check for S 0.96 for this pressure. So 0.96 is smaller than 50, as you can check. Okay, it's between 40 and 50, and you can get this temperature by doing interpolation. Okay, so if the temperature is 50, this means that I have some entropy generation, and that's why I have a larger value of S, which is 0.97. Okay, now I will consider, if you want, that it's isentropic, so I will stick to this value. And in case the temperature is given, you can just update the value of H and take to 84.39. Okay, now in case S1 equal S2, to be able to get the value of H2, you just interpolate between 40 and 50, and you say that since S is 0.96, but it's closer if you want to 50 degrees, and the value of your H2 will be close to 284.39. It will be maybe around 280. Okay, so this is how we can get properties at points 1 and 2. Now, going back to our figure, if you want to illustrate the process, so this is T, this is S. So we were able to verify that the compressor process is taking place in the vapor zone. And this is the reason why we use a compressor instead of a pump. Okay, so for point 1, which is, so this is the low pressure line. For the low pressure line, we have a pressure of 100 kilopascal. And our inlet point is in the superheated region. So this is point 1, which correspond to compressor inlet. Now, as we mentioned, it depends on the given. If the given will provide you with H2, okay, then you can verify that you will not have an isentropic process. So if I want to put the two processes here for comparison, let's say this is the 800 kilopascal pressure line. If I model it as isentropic, then the point should be on the vertical line. So I go up vertically. Okay, and this is point 2, which is the exit of the compressor. While in case I have some entropy generation, then I will have this. So instead of going just straight, let me change the color. So in case if it's not isentropic, I will have, let's say, a line like this because of entropy generation. And I will have to deal with another 0.2 prime. But then I need an extra information. Okay. If you, I will not go over all of details. And already I think you know them from refrigeration. They can give you what we call the isentropic efficiency. Then you can find 0.2 prime. But now, for now, or I will give you the temperature at 0.2 that will allow you to get H2. Or if I don't tell you anything, then you say H1 equal to H2. I assume the process is isentropic. And now I was able to determine 1 and 2, which are the inlet and exit of compressor. Now, what will happen now at the exit of the compressor, I will enter my condenser. Okay, so this is what in these terms we say that we are reversing the positions of evaporator and condenser, because now heat will be rejected at the high pressure and high temperature. And this is our purpose. We want to extract heat from low pressure and low temperature and reject it into high pressure, high temperature level. So this is the level where we have Q dot out. And of course, to find Q dot out per unit mass, we need to know, we already know H2. Okay, we need to determine H at 0.3. Here they said, assume that at the exit of the condenser, you have saturated liquid. So this will simplify things, because if it's not saturated liquid, we need to go to compressed liquid tables. So they should provide us with compressed liquid tables. So since they said, no, it's a saturated liquid, so we just have to go to our table of saturated 134A and check for 800 kilopascal or 8 bar, what is the value of HF. So we just have to check for HF at this pressure. Okay. So now, if we go to our tables, now we should go to the saturated tables of 134A refrigerant. So this is the table of saturated refrigerant, and we check for 8 bars. So it's here. Okay. So this is the line. This is the line of 8 bars. Okay. What we want is HF. So this is the column of HF. Okay. So we can read for this pressure, what is the saturated liquid enthalpy? And then it's here. So 8, it's 93.42 kilojoule per kilogram. And we can say that H at point 3 is equal to H at point 4 equals to HF, okay? Because we have the throttling process. And from the givens, I told us that, well, we can assume this process as process at constant enthalpy. So this will allow us to determine the condition at the exhaust of the throttle valve. Okay, so now okay, let us just I will just repeat the drawing in a fast way. So now we have all of our points. Okay, so this is our dome. Our first point was in the superheated region for the low pressure point, low pressure level, high pressure level. So this is point 1, isentropic process until point 2. They told us that we left our condenser at saturated liquid 3 and we calculated H3. Now, since in the throttling valve H3 equal to H4, so this will allow us to determine the condition at the exit of the throttling process. All we have to do, we know H4, H4 equals to H3. And we have that we are entering the evaporator and we'll have change of phase here. So it will the change of phase will continue until reaching point 1 and the cycle will repeat. So we need to determine the quality here at this point in order to get, if you want, let's say we want to calculate after maybe other properties than H, if we need the internal energy, if we need the entropy, any other property at this point, we need the quality. So to define the quality here, all we have to do is we go to the saturated tables. We say at 100 kilopascal, we can check for the values of HF and HG. And then we can calculate the quality at this point. We can do it together now. So we can get the quality at the exit of our throttling valve. And then we'll have the evaporation process here. The evaporation process will have this is what is more important for us. And the most important region for us is here, because this is where we will extract heat from our refrigerator. So we'll try as much as possible to, in order to enhance the efficiency, we try as much as possible to reduce H4. Okay, so to do this, you can condense more. And if you can exit the condenser at a compressed state, it's better, because if you are able to do this, then you will enter your evaporator at a lower quality. Okay, and as you do this, you will increase the value of Qn. Okay, so this is how you can enhance the efficiency of your system. You try to condense more to a lower temperature, and then this will allow you to reduce the quality at the exit of the throttling and enhance the heat extracted from your refrigerator. So this is an overall the problem. You can see that we have a lot of common features between refrigeration and power plant cycle. It's the reversed way, if you want, because instead of putting heat to extract work, we put work to extract heat. And from the properties of points, of course, I know that you might forget and know how the throttling valve will operate, that H3 equal H4. I know this. So in case I want to give you anything new, I will remind you in the problem. I will tell you in the throttling process, assume the enthalpy will not change. Okay, but just I just consider that, of course, you know, the compressors, the evaporators, the condenser, how they operate. Then you will be able, from the given, to build your diagram and then to answer all questions after. Okay, any question on this?
Yes, doctor, I have a question, please.
Yes, tell me.
First, the tables will be given in the exam, or it's
Yes,
on us
yes, I will
to
give you
make it?
tables, of course. Of course, I will.
Okay.
Okay. You,
Secondly, usually we count that at the outlet of the compressor or the pressure or the pump,
yeah.
the refrigerant or water is saturated liquid, right? Not vapor or saturated.
If you are talking about the compressor, you mean?
Yes. No,
The
at the outlet,
compressor,
usually we count that the fluid is
it can be
saturated.
superheated also. Okay. In this example, at the outlet of your compressor, you have superheated state. And once you enter the condenser, you will go first from superheated state to saturated vapor. And then the condensing process will continue. It can continue until 3 or can continue furthermore.
Okay.
Okay. So
Okay,
you
thank you.
can play with this يعني in general, but in general it's advised to enter the compressor. The inlet point can be a superheated vapor, but not it's not advised to have the inlet of your compressor in the change of phase zone. So you can you have cases where you enter at this level here at this point. So you will have, in this case, the inlet of your compressor will be a superheated vapor, saturated vapor, sorry, and the outlet will be superheated vapor. Okay. While when you talk about a pump, in the pump you should have an inlet of saturated liquid in order to not harm your pump. So the pump and compressor work in different regions. Pump is designed to work in a liquid state, while a compressor is designed to work in vapor state.
Okay, thank you.
Welcome. Other question? Okay. Now we can start to find the important properties here. Okay, so after finding H1, H2, H3, and H4, we can say that the COP, if they ask for the COP of the system, COP refrigeration is equal, as we mentioned, to Q dot N over W dot N. So the COP, you know that here the mass will cancel out the mass flow rate because it will appear in the numerator and denominator. So it's m dot, since it's the same flow rate that is circulating, not like the case of the regenerative Rankine. So here you have the same mass flow rate that is circulating everywhere. So you have m dot for Q dot N, it's between points 1 and 4. So it's H1 minus H4 over m dot times W dot N is between points 1 and 2. So it's H2 minus H1. So now all we have to do, we just replace our enthalpies, and that will cancel out. We can calculate the COP. Okay. Now, this same system can be used in HVAC applications. So I can give you an HVAC application and heat in case of heating. If you want to heat your space, then the COP will be, instead of Q dot N, it will be Q dot out. And then you will replace Q dot out by M dot H2 minus H3 over M dot H2 minus H1. Okay, so this same cycle can be used in several ways. And we can ask you also, for example, what can you suggest